Hello, thank you. Um, yes, I will start and will explain you a little bit what Mabanaft is doing in the area of new fuels and try to give you a perspective on the fuels of the future, as we call it. And hopefully it has a relevance for you because, of course, many of you will need to store these products in future. Maybe to say a few words about Mabanaft for those who don't know us. We are also part of Marquardt and Baus Group and leading independent integrated energy company. Our main business is providing energy solutions to our customers. So we are an energy supplier as we see ourselves, currently mostly liquid energy, but in future it of course can change. And we also decided that we want to proactively engage in the energy transition and to contribute to this and help our customers to move to cleaner new world faster. A few numbers: we are around about 1,000 employees, over 600 service stations, mostly in Northwest Europe, 18 million tons of sale volumes. And as you can see, our logo is green. It has always been green, even before it became popular. And now, of course, we need to also adjust our business to fit this nice green color. But I think we are on a good way to do so. One of our areas of activities is called New Energy, Chemicals and Gas. Here we focus a lot on sustainable fuels. I will explain it a little bit more in a second, but also chemicals is part of our portfolio. We are constructing one of the largest ammonia plants in the United States right now, where oil tanking slash Advario is also part of this project and is building the largest ammonia tank there to store this product. And finally, gas is also part of this new energy business where we trade LPG and bring it to our customers. So as we see, the future is not only about hydrogen. Of course, hydrogen will have a huge impact on energy transition and will be a key for the long-term energy transition. But apart from hydrogen, we also see a lot of future and potential for liquid products as well. And that is a good news because the entire infrastructure we all have now can be used in future as well for advanced biofuels, waste-based biofuels basically, and synthetic fuels produced or derived from hydrogen. You can get to the same products we have today from fossil fuels through different pathways. You can use biomass and ideally waste biomass to get to diesel, jet fuel, gasoline, whatever you require, even feedstocks for the chemical industry. But you can also produce your hydrogen through electrolysis process and then either use hydrogen directly or go to the synthesis process where you combine hydrogen with CO2 and in this way also get to these liquid or gaseous products. So more or less the same molecules but produced in a green way. We focus a lot now on e-fuels, the synthetic fuels, because we see these huge advantages of these products. They have more or less the same chemical composition as the products we already now use and know. The entire import or handling infrastructure can be used without any adjustments or changes. Also, our customers don't need to change anything on their cars or engines. They can just use synthetic fuels instead of fossil ones. And of course, they have a very high energy density. It's a liquid material. You can transport it better. You can store it more efficiently. And of course, you can bring it all the way to their customers and consumers, at the service stations without any modifications required. For that, we have different projects and initiatives. One of the largest initiatives is our joint venture P2X Europe with their partner, another German company, Hansen and Rosenthal. And one of the key areas of activities is development of our own synthetic fuels production. We are now planning a plant in Iberia to produce synthetic jet. But first of all, we are, as we speak, taking into operation a small demonstration plant in Hamburg. It will be producing synthetic diesel, hopefully in the next weeks already. And we hope to bring this product to the market this year. And the purpose of this small project is to demonstrate that the production and utilization of these synthetic fuels is absolutely realistic and possible. Our partner already operates a green electrolyzer in Hamburg for the last 3-4 years. It's around 5 megawatt of electrolyzer capacity, and now we're adding a small synthetic plant to that to combine green hydrogen with CO2 from biogenic source and produce synthetic products such as diesel, naphtha, and waxes. So yeah, we hope to showcase e-fuels very, very soon, as probably the first mover in Germany at least, maybe in Europe. Being able to offer it in the market basically in a commercial way. A very small volume, of course, but still it's important because we still lack a lot of legislation, we still lack a lot of clarity around how these products will be handled, how they will be, for instance, applied to the CO2 obligations we have as a marketer of fuels in Germany. So we hope to push a little bit the politicians to create this clarity finally. Well, moving on to hydrogen, we also see a lot of potential, of course, and this is a bit farther away from our current capabilities, but we believe that Mabanaft is also very well positioned to play a role here. And we all know that there is a huge potential for hydrogen. There are different forecasts, as we have seen today and during the first day of this event. And there will be importers and exporters. So, of course, there are regions where hydrogen, or particularly green hydrogen, can be produced in a more efficient way. Here, I just listed a few examples. Also, there will be regions where production of green hydrogen is not so efficient. I think in Northern Europe, particularly in Germany, or let's say Scandinavia, maybe is a bit different story, but here in the Netherlands or in Germany, it is more efficient, of course, to use green energy produced here directly. But the green energy demand will be so huge that you will also need to import it from the regions where you can make it more efficiently, and maybe where otherwise this potential for green energy will be underutilized. And this can be done in form of hydrogen or e-fuels or other materials, but one way or another it will need to be imported, and then the corresponding infrastructure will be required. How exactly you do this, how you transport hydrogen? The answer is simple. It depends, right? It depends. We are doing now a study with Technical University of Hamburg. We are taking part in different hydrogen initiatives, and everyone is looking into this, of course. And what we find out, I think, is that different ways and modes of transportation will be required and will be used, and it will depend a lot on how far you need to transport hydrogen. It will depend a lot on what is the final requirement. Do you want to use it as a liquid hydrogen, as a gaseous hydrogen? Do you want to use it as ammonia or methanol? The entire value chain needs to be analyzed, and then the decision has to be taken. I will show you a little bit more detailed comparison of these different ways to transport hydrogen in a bit. But I think over long distance you will use, of course, pipelines or ships, and on a shorter distance for distributed locally you will need some trucks or maybe railway to transport it, but it's of course much less efficient and will mean more losses during the transportation. But I think this is the main challenge all of us are facing now to understand this better. Before I show a short comparison of all these different methods to store and transport hydrogen, just a few words on what Mabanaft is doing. We are a founding member of Aquaventus. It's a large initiative in Germany to install 10 gigawatts of wind energy offshore and to produce hydrogen also offshore on the platforms. I think it's a bit still a nice idea with a lot of large companies involved. So, but it's rather a long-term development. Then we are also taking part in H2 Decentral. It's an initiative of German Energy Agency looking into decentralized utilization of hydrogen. And we also have some interesting local projects all around Germany looking into different opportunities to use maybe locally produce or store and use hydrogen. And finally, and this is why Claudia Hain is also here, Nacompex, it's our investment where a new hydrogen storage technology, or not so new actually, but Claudia will explain, but an interesting option to store and transport hydrogen is being developed. And before I hand over to Claudia, maybe a few words on different options to store hydrogen. Of course, you've heard about all of them, and as you see, all of them have a lot of pros, but even more cons. So you will need to compare very carefully what is the best option for you, but I believe that all of them will be used because there are so many applications. Hydrogen is so flexible in its utilization that all these forms will be used one way or another. So just to run very briefly through them, gaseous hydrogen is of course very pure and the mainly required product. You don't need a lot of energy for compression as in case of other materials, but on the other hand, it's a very low volumetric energy density and transportation over long distances has not been tested much yet, and a lot of investment for construction of this infrastructure will be required. Liquid hydrogen has, on contrary, very high volumetric density, but on the other hand, you will need a lot of energy to liquefy. There are boil-off effects while you transport or store it. And again, there are no large transport vessels available yet. Another interesting option is LOHC. It's easy handling, of course. You can store it in normal tanks. It's not explosive or dangerous in that regard, but it requires a lot of energy for dehydrogenation. And again, there are no industrial scale facilities. We see some potential troubles with purification of hydrogen after you reconvert it back from LOHC. But on the other hand, there are some ideas to use LOHC directly as a fuel in engines, and then it might be an interesting option. Ammonia is kind of looks like one of the best options to transport hydrogen over long distance at this point. The advantage is that you just need nitrogen to combine with hydrogen. It's widely available. We know how to handle ammonia. Again, our friends from and colleagues from oil tanking have long years of experience with this product, as many of you probably. Ammonia might be used directly. A lot of shipping companies are now looking into ammonia as potential fuel for ships. But on the other hand, again, ammonia is a toxic product. There might be some cleaning effects if you want to reconvert it and use it as hydrogen. And on large scale, there are no crackers available yet. So again, a lot of infrastructure will be required to make this happen. And finally, methanol is another option. Again, it's a known product. You can store it. You have the entire infrastructure. It's easy to be handled. But on the other hand, you need CO2, a good source of CO2 to make it. And as the same problem as with most of the options on the lower side of this table, energy demand is quite high to crack it back into hydrogen. I think one more option missing here could be e-fuels. I also see it as another option to basically bring these green molecules from long distances to where they are required. Mabanaft is also looking into exciting projects like HEAF project in Chile, where green gasoline will be produced from hydrogen. And of course, in the liquid form, you can transport it much better and easier. But again, you have a lot of conversion losses. So it's only makes sense if you really have a location where a lot of green energy available and no local demand is there, and you need to transport it over a long distance. Then it might be efficient to do it in a liquid form. And finally, I think I hand over to Claudia. She will explain you another option we want to add to this list. It's in the development now, under development, but is a very promising and interesting technology. So Claudia, over to you.
Thank you. Hello to everybody. My name is Claudia Hain. I'm the CEO of Nacompex GmbH, and we're dedicated to storing renewable energies, which for us is electricity from solar or wind power mainly. I'm really glad to present to you our patented Ferrodox technology, which is a storing option for hydrogen as well as energy in general and electricity. Thanks to Oleksandr, we're really glad that Mabanaft is our investor and pioneers very much the energy transition in the oil sector. And I think this is the right time and the right opportunity to set it in reality, that we will find alternatives to fossil fuels in future. So our approach to storing energy is chemical energy storage. As we already learned from Catherine, today there is a huge storage demand in the energy economy. And this asks not only for underground bulk storage, but also for overground storage. And our Ferrodox technology is dedicated to this storage task. It's actually a very old industrial method known as the iron steam process that we took as a core and patented for the new tasks within the energy transition to store. In the middle, you can see an old reactor which was built in 1904 when hydrogen economy was already existing because of the Zeppelin industry, so actually a mobility task. And the task was, as well as today, to have a production method for very huge quantities, very cheap and robust for industrial application. On the right-hand side, you see a plant which was built in the 1970s in the GDR. Here, the same process was adapted in order to produce city gas, special gas compositions instead of natural gas, which was not available in the GDR. And as now the task is again to store huge quantities of energy or hydrogen, this technology has very good characteristics to form the right storage. So it's high volumetric density of about 800 norm cubic meters per cubic meter of storage. And it's low secondary energy consumption during the storage process. Form a very good storage component for different pathways of hydrogen economy. So basically you have a indirect hydrogen storage. That means via an reversible redox reaction, the hydrogen is kind of consumed, its chemical energy is stored, and then later on from the iron carrier material you can release hydrogen again when you need it. So this is the core process, and I want now to introduce you to the process scheme. So basically, you see the storage itself in the middle, and it works together with the water electrolyzer, which is, of course, the component in the systems to transform electrical energy into hydrogen. And we want to load the storage by producing hydrogen, loading it, going with the hydrogen stream to our iron mass bed. And the hydrogen will take from the iron oxide, the oxide component, produced steam that can be condensed and then as water led back to another cycle of the electrolyzer. If you could apply a high temperature electrolyzer, then you could also directly use the steam from the storage loading process in order to perform the next cycle of steam electrolyzers. That leads to a very high efficiency because you won't have any emissions from that. The oxygen component is liquefied and stored later for the unloading of the storage. So this is basically the loading. The unloading would work, for example, this is dedicated to produce electrical energy in the end via a fuel cell. The fuel cell is driven by hydrogen steam mixture that comes out of the storage while unloading. And it is burned within the fuel cell together with the stored oxygen, and it forms steam again that is led back to the reactor to perform another unloading cycle. In this way, you would have a very good input power to output power ratio, which makes it very suitable for electricity storage. But of course, you could also use this as hydrogen storage. If you just take off the hydrogen from the right-hand side and take fresh water from the left side for loading, so you could also use it for chemical storage. This basically is the concept of the Faradox technology, and it, due to its closed cycle without emission, it leads to very high overall efficiencies, especially with high temperature electrolyzers and fuel cells. But the process can be seen in very various applications, which I collected for you, which is in the first bulk hydrogen storage. You would have no pressurized tanks needed for it, so you have only a low heating energy consumption of the storage process, and you can take out 100% of the hydrogen stored before. That can be applied to transport tasks as well as local storage in production processes, and of course the purity of the hydrogen is very well, so this might be used in the future for chemical production to form a new basis chemical. You can also use it, as shown in the process scheme, for decentral electricity storage, which is as well needed in the energy economy. And last but not least, the process, as patented, is also suitable to transform CO2 into CO via the unloading cycle. That means it's perfect for all situations where you want to produce synthesis gas for synthetic hydrocarbons. So in all these applications, you could find Feradox as a base technology, and it has some advantages to the other options Oleksandr already introduced. And we are ready to develop reference plans within these applications. We are, as a technology provider, offering our services to planners and applicants in this field. Thank you. And if you have any questions, I can tell you.
I think I have one more slide to finalize. Thank you, Claudia. And basically, this is a short summary of what we have explained about, because we were supposed to talk about fuels of the future. So we think that, of course, green hydrogen will play an important role. And for that, maybe to give you our perspective on infrastructure requirements, a new infrastructure will definitely be required. We still need to see what exactly, in what way hydrogen will be transported. Probably all these possible means of transportation will be used. So you will need ammonia storage, you will need hydrogen storage, you will need conversion capabilities, and of course entirely new distribution infrastructure as well. On the other hand, for biofuels and synthetic fuels, we see the requirement for smaller segregated tanks, because there will be different qualities of these products, particularly on the advanced biofuels side. You will see different products, different qualities, different also kind of certifications which you will want to kind of store separately and segregate. So we will need more flexibility definitely on the storage side. And also specific blends will be required for different customers and applications. Again, you will need probably smaller tanks to accommodate this requirement. And for the synthetic fuels, the advantage is they're a bit more unique, a bit more heterogeneous, so they're very similar to fossil fuels. In that regard, you can use the same tanks. On the other hand, initially they will not be used, of course, as pure fuel because of the cost, I guess. But with the scaling up and the cost decrease, I think they will take over and they will replace the currently existing fossil fuels. We believe they have a lot of future, despite the electrification in the transportation sector. We will see millions and millions of combustion engines on our roads and in our machinery for decades to come. And all these engines will also need to be decarbonized, and this is a very good way of doing so. But all in all, yes, we will need a lot of changes in the infrastructure. The good news is liquid tanks will also be required, maybe in a bit more flexible way. And we will need a lot of new infrastructure for hydrogen in different forms. And maybe Feradox technology will also play a role. We hope so. Yeah, thank you very much. I think that's it from our side, and we're happy to answer your questions now or later during the panel discussion.
We have a question.
Thank you for a fantastic presentation. I think this was really groundbreaking work that you have done. And everybody will think, why haven't we thought about it? Just a very simple question. The relationship between you two, so Feradex, Mabanaft, is Mabanaft fully owner of Feradex, or is it just a stakeholder in the company? And if we would want to talk to Feradex, is that possible? Have we to approach Mabanaft, or do we have to approach you?
Okay, so yeah, we are an investor, a stakeholder in the company. It's not fully owned by Mabanaft, and now basically our investment unlocked certain subsidies as well to build the first test plants and to test the technology. but we work very closely together. Basically, Feridox or Nacompx is the technology developer. Mabanaft is the one who will be commercializing and bringing this technology into commercial applications or helping Nacompx to do so. So you are welcome to approach either Claudia Hain and her colleagues directly, or Mabanaft. We are happy to discuss the opportunities.
Or maybe over a coffee.
Yep.
We're running slightly, but thank you both very much.